Hello, my name is Amber Moritz, and thank you for attending Thyroid Releasing Hormone and Thyroid Stimulating Hormone. Today we will have a brief overview of the endocrine system and the role of hormones within it, followed by a brief analysis of the effect a time lapse may have on the effectiveness of a hormone. The endocrine system is one of the major control systems of the body. It influences metabolic processes via the regulation of chemical messengers called hormones. Hormones are responsible for the initiation, progress, and cessation of natural processes such as reproduction, growth and development, electrolyte, water, and nutrient balance in the blood, cellular metabolism, and the mobilization of body defenses. Unlike the nervous system, the endocrine system initiates slow, long-duration responses that can be enacted anywhere the blood can reach, including over long distances. The endocrine system contains two kinds of glands, exocrine and endocrine. Exocrine glands produce non-hormonal substances such as sweat and saliva, and those substances are carried to membrane tissues via ducts. Endocrine glands have no ducts, but instead produce and release hormones into surrounding tissue fluids for transport. Endocrine glands include the pituitary, thyroid, pineal, and adrenal glands, as well as neuroendocrine organs such as the hypothalamus. Though not technically a gland, the hypothalamus secretes hormones. There are also several organs that contain concentrated endocrine tissue, such as the pancreas, gonads, and placenta. Hormones circulate to all tissues, but only affect the performance of tissues with the appropriate receptors. They alter the normal processes of the tissue, slowing or increasing the rate at which cells perform their functions. Hormones may produce one or a combination of the following changes: the opening and closing of ion channels, altering membrane permeability and/or potential, the stimulation of synthesis of proteins and enzymes, the activation or deactivation of enzymes, and the induction of secretory activity. It may sound circuitous, but many endocrine glands release their hormones in response to hormones secreted by other endocrine organs. This hormonal stimuli is how the foci of our attention, thyroid releasing hormone and thyroid stimulating hormone, are circulated in the body. Thyroid hormones control your metabolism, heart rate, body temperature, digestion, strength, and cell regeneration. Fluctuations in the amount of thyroid hormones available in the body sends a message to the hypothalamus, which releases thyrotropin-releasing hormone, which then activates the anterior pituitary to release thyroid-stimulating hormone, inducing the thyroid to liberate more thyroid hormones. Because thyroid-stimulating hormone acts on an endocrine gland to produce another hormone, it is called a tropic hormone. Because the hypothalamus secretes TRH to act on the anterior pituitary gland to produce another hormone that acts on yet another endocrine gland, it is called a hypophysiotropic hormone. Thyroid hormone itself is actually comprised of two different hormones, triiodothyronine, or T3, and tetraiodothyronine, also known as T4. Thyroid hormone doesn't have a target organ and instead affects every tissue of the body. It crosses the plasma membrane and binds with intracellular receptors, altering the transcription of mRNAs and thereby the synthesis of proteins that carry out cellular responses. These hormones regulate our overall basal metabolic rate, or the rate at which the body consumes oxygen and expends energy under resting conditions. They also have an effect on the body's calorogenic rate, or the rate at which it produces heat. An increased metabolic rate results in an increase in heat production. Thyroid hormone also stimulates the secretion of growth hormone and insulin-like growth factor 1, which mediates the effects of growth hormone. In 2022, Kristen Thayne, Cassandra Uricchio and Nicholas Frank conducted an experiment to see if a variable time lapse had any effect on the effectiveness of TRH in stimulating the release of another hormone, adrenocorticotropic hormone, or ACTH. The TRH stimulation test is a trusted method of diagnosing pituitary pars intermedia dysfunction, or PPID. PPID, previously known as equine Cushing's disease, is a condition common in older horses and is associated with laminitis, endoparasitism, chronic infections, and behavioral changes. The TRH stimulation test involves stimulating the release of ACTH by intravenously injecting TRH. Horses with PPID will have an exaggerated release of ACTH because of TRH receptors located within the hypoplastic tissue of the pars intermedia of the pituitary. Determining if there is any change in release of ACTH dependent upon the sampling time could help improve the early detection of PPID and reduce the risks of false negatives due to imprecise sampling times. 24 healthy adult horses that had been housed for a minimum of 1 year under controlled circumstances were chosen for the study. All were untested for PPID, but approximately a quarter of the subjects showed symptoms attributable to the condition. The subjects ranged in age from 3 to 28 years and included 9 mares, 14 geldings, and 1 stallion, distributed across 8 different breeds. Testing was performed in December and January of 2019 and 2020, with the last 8 horses being tested in December of 2020 due to COVID restrictions. Testing was conducted between 8 a.m. and 10 a.m. and completed within 20 minutes for each subject. A 1 milliliter dose of commercially synthesized TRH was injected into the right jugular of each subject, and collection of blood samples was timed. Samples were taken before TRH injection at 0 minutes, 9 minutes after injection, which is 1 minute early according to procedure, at 10 minutes, which is the standard time dictated by procedure, and at 11 minutes, which is considered 1 minute late. 2 samples were taken at the 10-minute mark to account for intra-assay variability. Blood was collected sequentially from a single puncture site to minimize trauma, and all samples were then frozen to be analyzed within 40 days from the time of collection. Samples were centrifuged, and the plasma tested for ACTH concentration by chemiluminescent immunoassay on an automated analyzer. The 2 samples at 10 minutes were averaged to account for variability of concentrations within the 10-minute mark. As shown in the figure, all horses showed an increase in plasma ACTH concentration after administration of TRH, with most horses exhibiting maximum ACTH concentrations at 9 or 10 minutes. At 9 minutes, 7 horses, or 29% of the subjects, were positive for PPID with ACTH concentrations greater than 200 picograms per milliliter, while 3 horses, or 12.5%, showed an equivocal diagnosis with a concentration between 110 and 200 picograms per milliliter. At the standard testing time of 10 minutes, only 6 horses showed with concentrations greater than 200, and only 1 reached the equivocal value. Based on these measurements, 5 horses would have changed PPID status with early or late sampling. As you can see, 2 horses would have shown positive for PPID at 9 minutes, but equivocal at 10, and 3 other horses showed equivocal at 9 minutes, but negative at 10. From the 10 to 11-minute mark, there were no status changes, though there were several sharp declines in ACTH concentration. These graphs show the correlation between 10-minute standard ACTH concentration and magnitude of variability with early or late sampling during the TRH stimulation test in 24 adult horses. Variability is reported as percentage difference in the measured value compared to the paired 10-minute standard value for each collected sample. As you can see, Early sampling values are represented by circles and the solid trend line. Late sampling values are represented by triangles and the dashed trend line. Graph A shows an analysis of all data. B shows results from only those horses with an ACTH concentration of less than 250. As you can see from figure A, the magnitude of variability over all the data does not vary much with either late or early sampling. However, figure B shows a larger discrepancy or instance of variability across those horses that would be deemed equivocal or negative for PPID. Overall, it was discovered that even small alterations in the timing of sample collection can significantly alter the concentration of ACTH in the blood. 75% of the subjects had at least one early or late sample result that differed by more than 10% from the 10-minute standard. In 25% of the subjects, both the early and late values differed by more than 10% from the 10-minute standard. 21% of test subjects had different test interpretations associated with late or early sampling, meaning their PPID status changed depending on when the sample was collected. Though some natural variation in ACTH concentration is expected, the TRH is expected to stimulate maximum ACTH production and should overwhelm any small variations that may occur naturally. Previous studies concur that peak ACTH concentration happens in less than 15 minutes, though the precise timing varies from study to study, and increased sampling does not improve diagnostic accuracy. This is likely a result of differences in drug metabolism and the individual responses of the subjects. Though previous studies did not include the effects of single-minute differences in sample collection times, these results indicate that minor variations in the timing of sample collection can have significant effects on test results and their diagnostic interpretation. Thank you. And this has been thyroid stimulating hormone and thyroid release hormone.